Welcome back, Design Junkies, to Mechanical Engineering Made Simple. We are cracking open a pretty hefty stack of technical sources today. We're really going to dive deep into the architecture of power transmission. We're moving past just, the idea of a spinning wheel and getting right into precision gear design, covering everything from basic tooth definitions all the way to complex material stress factors.
Exactly. Our mission really is to boil down this mountain of data,
Hmm.
extract that foundational knowledge you absolutely need to understand, and, crucially, to design truly functional, high-precision gears. We're aiming to build a complete engineering blueprint, moving step by step from basic categories right through to what makes a gear last.
And before we get totally lost in the weeds, there's something really critical that jumped out from these manuals. It kind of sets the tone for everything else. The goal isn't just making gears that work. The sources really hammer this home. Modern engineers have to aim for perfect gears right from the start.
That's absolutely the key takeaway here. The material is really insistent on this. If you ignore the advances in, well, scientific gearing theory, if you just simplify things too much at the beginning, you end up with what they call approximate gears. And these approximate gears, they just inherently can't meet today's needs for high power density, low noise, low vibration. That perfection has to be designed in from the get-go.
Okay, so let's unpack this blueprint. Starting at the highest level, the basic classification. How is the whole world of gears first divided up?
Based on their axis, right?
That's right. It all comes down to how the axes of rotation relate to each other in space. Three main families. We start with the most straightforward, parallel axis gears. The driving gear's axis and the driven gear's axis are perfectly parallel.
And the big one here, the most common, that's the spur gear, isn't it?
Correct. It's cylindrical, teeth are straight, run parallel to the axis. It's the easiest to manufacture, most cost-effective, definitely the workhorse. But right alongside it, you have the helical gear. Still cylindrical, but the teeth are cut in a helix like a screw thread. Okay, and the advantage there?
Well, it gives you smoother, quieter power transfer, and it can generally handle a higher load than a spur gear of the same size.
Sounds like a direct upgrade then. Why not use helical gears for everything? What's the catch?
The catch is axial thrust. That helix angle, it creates a force that pushes the gear sideways along its axis. So you need bearings designed to handle that thrust.
Right.
Engineers found a way around that too with the double helical gear. Imagine two helical gears, one with a right-hand helix, one with a left hand, machined back-to-back on the same shaft. The opposing helix angles cancel out the thrust forces perfectly. Think herringbone pattern.
Clever. And there is one more in this family.
Yes, the internal gear. Here, the teeth are cut on the inside surface of a ring. It often meshes with the standard spur gear. You see these a lot in planetary gear systems for compact speed reduction.
Got it. Parallel axis family. Spur, helical, double helical, internal. Makes sense. Okay, category 2. Intersecting axis gears.
Right. Now, the axes cross, typically at a 90-degree angle, though other angles are possible. This is mainly the bevel gear family. The simplest form is the straight bevel gear. The teeth are tapered, like sections of a cone. It's the easiest bevel gear to produce.
So, the spur gear is to parallel axes. The straight bevel is the basic for intersecting axes.
Pretty much, yeah. But if you need higher performance,
There's always something better.
usually. In this case, it's the spiral bevel gear. The teeth are cut along a spiral curve on the cone face. This gives you significantly higher strength and much, much quieter operation compared to the straight bevel. But, as you'd expect, manufacturing is way more complex.
Okay. Spiral for strength and quietness. Is there anything else here?
There's a sort of hybrid called the zero bevel gear. It's technically a type of spiral bevel gear, but it's designed with a zero spiral angle. So it shares the force characteristics of a straight bevel, no significant thrust loads, but keeps some of the smooth meshing benefits of the spiral tooth form. Kind of an interesting middle ground.
And the final family. The ones that break the rules. Crossed axis gears. Neither parallel nor intersecting.
Exactly. These axes exist in different planes and would pass each other if extended. This category is often about achieving really high gear ratios. The classic example is the cylindrical worm gear pair. You have a screw-like worm driving a helical-like worm wheel. Its main advantage, its standout feature, is getting a massive gear ratio in just one single mesh, often 50.1, 100.1, or even more. Plus, it's usually very smooth and quiet.
Sounds amazing. High ratio, quiet. Oh, what's the downside? There's always a downside.
Efficiency. The transmission efficiency is generally poor compared to other gear types. There's a lot of sliding friction between the worm thread and the wheel teeth, which generates heat and wastes energy.
Okay, efficiency is the trade-off for that huge reduction.
Got it.
So that covers the main classifications. Now let's move from the big picture down to the nitty-gritty. Designing that perfect gear, we need the language of precision, right? The sources call out three core concepts for tooth dimensions.
Absolutely crucial. These three define the tooth's basic geometry. First up is the module M. Think of the module as the fundamental measure of tooth size. It's a metric unit. In the English system, it's related to something called diametral pitch, which is teeth per inch of diameter, but module is simpler conceptually. Bigger module, bigger teeth.
Okay, module equals tooth size. What's next?
Next is pitch. If module is size, pitch is the spacing. Specifically, it's the distance along the pitch circle between the same point on adjacent teeth. And the key thing is reference pitch P is directly calculated from the module P equals pi times M. So the absolute fundamental rule for any two gears to mesh correctly is they must have the same pitch, which means they must have the same module.
Makes sense. Same size teeth, same spacing. And the third concept?
The pressure angle, alpha. This is the angle between the line of action, the direction the force pushes between teeth, and a line tangent to the pitch circles. It defines the shape of the tooth profile. Standard pressure angles, like 20 degrees, are common to ensure gears from different manufacturers can potentially work together. It affects strength, contact ratio, all sorts of things.
Module, pitch, pressure angle. The building blocks. But making these things isn't perfect. The sources really flag there. Undercutting is a major issue, especially with smaller gears. Pinions specifically. What exactly is that?
Undercutting happens during the manufacturing process, typically when using a hob cutter to generate the teeth on a gear with a small number of teeth like a small pinion. The cutting tool essentially scoops out too much material near the base, the root of the tooth. It cuts deeper than where the mating gear tooth profile would actually contact.
And that weakens the tooth.
Severely. It removes critical material from the dedendum area, right where the bending stresses are highest. It creates a stress concentration point and makes the tooth much more likely to just snap off under load. This is exactly the kind of flaw you get with approximate geometry.
Okay, so how do engineers prevent this? How do you make a strong, small gear without this undercut?
They use a really elegant technique called profile shifting, or sometimes just correction. The analysis shows that for that common 20-degree pressure angle, if you have 17 teeth or more, you're generally safe from undercut. But if you have 16 teeth or fewer, you're in the undercut risk zone. The fewer teeth, the worse it gets.
So the correction fixes this.
Yes. You apply what's called a positive correction. This involves intentionally feeding the gear cutter slightly further out from the gear center than the standard depth. It effectively shifts the whole tooth profile radially outwards, moving the critical root section away from the damaging part of the cutter's path. It prevents the scoop out, the undercut.
That's clever. You're basically adjusting the manufacturing process to enforce a stronger geometry at the tooth base. Does this profile shifting do anything else?
Yes, and this is where it becomes a really powerful design tool. It's got a dual purpose. Besides preventing undercut, profile shifting is also used deliberately to fine-tune the center distance between two mating gears. Let's say your design needs a very specific distance between shafts, and the standard module and tooth counts don't quite hit it. You can apply specific amounts of positive or even negative correction to one or both gears to precisely adjust their operating center distance.
So it's not just fixing a flaw, it's also a precision adjustment tool. Very neat.
It's fundamental to high-precision gear design.
Okay, let's zoom out again. From a single pair of gears to whole systems gear trains, how do we figure out the speed changes in direction when we link multiple gear pairs together?
Well, a simple meshing pair is what we call a single-stage gear train. When you connect these in series, say the output of the first pair drives the input of a second pair, you have a two-stage gear train, or multi-stage if there are more. Calculating the overall speed ratio, often denoted by I, is actually pretty simple. It's just the product of the individual stage ratios. So I total equals I stage 1 times I stage 2, and so on.
And what does the value of I tell us?
If I is greater than 1, it's a speed reduction. The output is slower than the input. If I is less than 1, it's a speed increase. And if I equals 1, well, speed is unchanged, maybe just changing direction or transmitting power.
Speaking of direction, what are the rules there?
For standard external gear meshes, like two spur gears or two external bevel gears meshing, they always reverse the direction of rotation. Input clockwise means output counterclockwise. However, if you use an internal gear mesh, where one gear's teeth are on the inside, then the input and output shafts rotate in the same direction. That can be useful sometimes.
Okay, simple multiplication for ratios, reversal for external gears, same direction for internal. Got it. Now, here's something that always seems counterintuitive, especially after talking about perfection. Backlash. The sources say we need it. Why design looseness into a precision system?
Right, it does seem odd at first. Backlash is basically the small amount of clearance, or play, between mating teeth. It's defined as the amount by which the width of a tooth base exceeds the thickness of the engaging tooth on the pitch circle. And it's absolutely essential. Think about it. Gears aren't perfectly made. They heat up and expand when running. Lubricant needs space to get in between the teeth. Without that tiny bit of backlash, the teeth would bind up instantly. You'd get interference, massive friction, overheating, noise, and likely very quick failure, jamming.
Okay, so it's a necessary evil, maybe. How is it normally created? Do you just mount the gears slightly further apart?
You can increase the center distance slightly to create backlash, but that's often less precise and can affect the contact pattern. The more common and generally preferred method is to intentionally make the teeth slightly thinner than their theoretical size during manufacturing. You reduce the thickness of each mating tooth by a small, calculated amount. The total reduction across both teeth creates the desired circumferential backlash, usually denoted JT, right at the pitch line.
So you control it by removing material from the teeth themselves.
Exactly, and controlling it is critical. Too little backlash and you risk jamming, pulsating transmission, overheating. Too much backlash and you get excessive noise, impact loads when direction reverses, and potentially faster wear. It's another one of those critical details for perfect operation.
Okay, backlash is essential clearance, controlled by tooth thinning. Now let's shift focus completely. Materials and longevity. What are gears actually made of, especially for demanding applications?
For high-performance, high-strength gears, we're almost always looking at alloy steels.
Right.
Things like SCM 440, which is a chromium molybdenum steel, or S45C, a medium carbon steel. But the key thing is the steel itself is only part of the story. The real performance comes from heat treatment. That's what unlocks the required strength and durability.
What kinds of heat treatment are common?
The sources highlight two main approaches. First is thermal refining. This typically involves quenching rapid cooling followed by tempering at a relatively high temperature. This gives a good balance of through hardness and toughness for the entire gear body.
Okay, balance properties. But what if you need extreme surface durability, like where the teeth are constantly meshing under heavy load?
Then you need a surface hardening treatment. The gold standard is carburizing and quenching. You introduce extra carbon into just the surface layer of the steel, then you quench it. This creates an extremely hard outer case. We're talking Vickers hardness of maybe 600 to 640 HPV, while keeping the core of the tooth tougher and less brittle. That super hard surface is fantastic at resisting wear and pitting fatigue, which are common failure modes right at the tooth flanks.
Makes sense. Hard surface, tough core. Now, steel obviously dominates, but we do see plastic gears too. What's the story there? Materials like nylon or acetal?
Right, plastics like MC nylon or acetyl copolymer, often called Duracon, have their place. Their big advantages are being lightweight, naturally self-lubricating to some extent, and operating very quietly. Great for noise reduction.
But they must have limitations, right?
Oh, definitely. Big limitations. The main one is dimensional stability. Plastics expand and contract a lot more with temperature changes than steel does. They also tend to absorb moisture from the air, which can cause them to swell. This makes holding tight tolerances, like for backlash, much trickier over different operating conditions.
And I bet they can't handle the same speeds or loads as steel.
Absolutely not. Their strength is much lower, and they're very sensitive to heat generated by friction. The sources give clear limits. For instance, even with continuous lubrication, a plastic worm gear pair made of MC nylon has a maximum recommended sliding speed of only about 2.5 meters per second. Push it faster, and it'll likely overheat and fail quickly. You can't just swap plastic in for steel without careful analysis.
Okay, so plastics are for lighter loads, lower speeds, where noise or weight is key. Finally, let's talk about keeping gears alive. Lubrication. It seems critical. What are the main ways gears get lubricated?
It's absolutely vital. Lubrication reduces friction, carries away heat, and flushes out wear debris. There are basically three common methods, scaling up with speed and load. The simplest is grease lubrication. Good for open gears or enclosed gearboxes running at low speeds. It sticks in place well, but it's not great at cooling.
Okay, grease for low speed. What's next?
For medium to reasonably high speeds, you typically use a splash or oil bath system. The gearbox housing acts as a reservoir, and the rotating gears dip into the oil, splashing it around to lubricate all the moving parts. The key here is managing the oil level carefully. Too high, and the gears churn the oil excessively, causing energy loss, agitation loss, and overheating. Too low, and you don't get enough lubrication or cooling.
Right, the Goldilocks zone for oil level. And for the really demanding stuff, high speed, high load.
That requires forced oil circulation. Here, you have an oil pump that actively takes oil from a sump, often filters and cools it, and then sprays it directly onto the gear mesh and bearings. This provides the best lubrication and, crucially, the best cooling for heavy-duty applications.
And regardless of the method, there's a critical temperature limit we need to respect.
Yes, a hard rule from the sources. Keep the oil temperature below about 80 to 90 degrees Celsius. That's roughly 175 to 195 Fahrenheit. Go above that, and you risk serious trouble. The lubricant itself starts to degrade rapidly, losing its protective properties. The gear housing might distort from the heat. And critically, thermal expansion can eat up your designed-in backlash.
Ah, the backlash decreases.
Exactly. And, as we discussed, lose too much backlash, and the gears start to bind, leading to rapid wear, potential jamming, and catastrophic failure. That 80-90C window is really the upper limit for safe, continuous operation.
Wow, okay. So that really covers the whole life cycle. That was an incredibly comprehensive look, really, at the whole mechanical engineering journey of a high-performance gear. We went from the basic classification through the nitty-gritty of tooth geometry and material science, all the way to lubrication and temperature control affecting its lifespan.
And the clear thread running through all of it is that achieving genuine high performance, meaning low noise, high power density, long life heart, it really is a masterclass in controlling errors. It boils down to meticulously managing those tiny geometric deviations, things like single pitch errors, run-out errors, while also nailing the big operational factors, like having the correct amount of backlash designed in and ensuring proper cool lubrication throughout its life.
Which brings us right back to that powerful idea we started with, that quote from the sources. No perfect gears can be designed and manufactured if advances in the theory of gearing are ignored. And that leaves a really interesting question for you, the listener, whatever your own field might be. How often are you maybe relying on approximate solutions, the way it's always been done, the easier path? Especially when there's likely a more detailed, established theoretical framework out there that could help you achieve true perfection, or at least much higher performance. What detailed technical manual, what foundational theory in your area might you be overlooking right now? Maybe it's time to go find it. We'll see you next time.